Hello, logic students. I'd like to make two videos on direct derivations. For this first one, I'm going to run through the rules we use for direct derivations. We have many more rules than what we have for simple derivations. And then I'll practice some exercises and show you these rules in practice in another video. Okay, so for derivations, right, you use rules or inference patterns to show that a conclusion of a larger argument follows from its premises. That when it might not be immediately recognizable, but you go through these steps of recognized inferences. So for simple derivations, we might have an argument P or Q, premise 1, premise 2, R implies not P, premise 3, R, and the conclusion Q. This is indeed a valid argument, but to show it, short of a long truth table, we go through a couple intermediate steps using recognized valid inference patterns, right? For simple derivations, we have modus ponens, modus tollens, and MTP, right? So since R is true and R implies not P, we can use the modus ponens pattern to deduce not P using lines 2 and 3 modus ponens. This is a simple derivation now. I'm going to get to the rules for direct derivations, just doing a recap on derivations. And then P or Q is true, premise 1, but line 4, P is false, therefore Q is true. From lines 1 and 4, MTP. Okay? We have a little different method of labeling with direct derivations because we have different rules. So let me run through that. Okay, so the rules we're going to have, they're still inference rules. One difference is that some of the inference rules are going to be what we call one-line rules. So you could take a single line and draw an inference from that one line. Now the way Hardegree sets this up is interesting. All of our rules either introduce one of our logical connector symbols like and or and make a larger statement using those symbols. So those are we call those in rules. How can you introduce an and into a statement? And we also have out rules, right? So you might have an and statement, right, like A and B, right? And you can see that we can immediately deduce from this, A and B are both true, we can deduce from this A, right? This is something we could have done in chapter 3 with our logical implication exercise, right? A and B certainly implies A, and this is going to be an out rule because we detach this part of the and statement, right, to get a new, to deduce a new statement. A and B is true, so we deduce A. This is going to be an example of an out rule. This is by line 1, and you just write the symbol and out. So it's a nice formulation. You don't have to memorize. I learned it with different names. This would have been called simplification, right? But you have descriptive names. You have either and in or and out. In this case, this is and out. You took an and statement and you detached half of it, right, leaving the and behind, so to speak. And so this is our and out rule. So let's run through these rules in turn. That'll be the main content of this video, and then I'll practice some inferences, some exercises, some derivations using these rules. So first we have the and in rule. So this is the and out rule. I'll get to in a second. Okay. Well, let's start with the and out rule. And the way Hardegree writes this is that you have the one or two premise pattern. Okay. And then below the line is the pattern of the inference you can draw. Okay, below that is the pattern of the inference you can draw. So, and now remember, A and B can stand for any statement, so it's a very general pattern. Any line where and is the main connector, because these are what we call whole line rules, anytime you have and as a main connector, you can extract half of it. In fact, there's two versions of this rule, because if you have an and statement, you can also detach the left side. Okay, you can also detach the left side. We're not doing equivalence rules in this class, but when I was taking this class in the late 1900s, right, to do this, you would have to use an equivalence rule to change A and B to B and A. And then, but we allow you to, any and statement, and is the main connector, you can detach either the left half or detach the right half. That is our and out rule. This is the and out rule. And out rule. Okay, remember A and B can stand in here for any statement whatsoever. They don't have to be a simple, right? So you could have something like P or Q and R, right? P or Q and R. You could use the and out rule to detach either half of this and statement around the main connector to get P or Q, and of course that could be useful for other argument forms, right? Now you have an or statement, you can use what's going to be our or out rule, which will be our new name for MTP, right? Or you could detach this R, which could be useful in lots of contexts. So any and statement, you can detach, you can draw an inference. Now, you can't do this at the same time, right? So if you had an argument A and B, move the screen here. If you had a premise A and B, right, let's take this argument. A and B, B implies C, therefore C, right? We won't get to the whole thing, but you can see modus ponens, right? If you could detach both, but one step at a time, okay? So line 1, so line 3 could be A from line 1 and out. Line 4 could also then be B from line 1 and out. And you'll see with these rules, you'll have a lot more options than you did with simple derivations. Some of them, right, for this derivation, you wouldn't necessarily need this step, but it's a perfectly valid inference using the rules, and so you'll get credit for it. You certainly won't be marked off, and indeed, if you don't finish your proof and don't get full credit, you'll get credit for any, as I say, legal inference that you do. So this is a perfectly good application of the and out rule, even if you don't need it later in the proof. This would be important. We'd use modus ponens. We'll have a new name for it, right, to get C, the next step. But you can do that one at a time. You have to do it one at a time, though. You're making a single inference. These are strict rules, right, according to the form. Okay, so there's your and out rule. Apologies, I won't be able to keep all these up with the limits of the screen here. We'll just have to run through these one by one. Okay, so we have the and out rule. I'll try to write them in a sidebar here. And an and in rule. And out. Take any conjunction and you can extract one half of the conjunction. Okay, there's our and out rule. Next we have and in. And in, right, is going to be a two-line rule, and it kind of works in reverse, right? You can take any two lines. Again, many more options here. Any two lines can be validly conjoined, right, as a conjunction, right? Any two lines. So the way he'll write the form is that you have two lines that say A and B. You can conjoin them. And remember, this applies to any two separate lines in any argument or derivation of the argument, right? As I say, you can smush them together, right? Take line 1, take line 5, put them both in parentheses, put an and in the middle, boom, you have the and in rule, okay? It can be very flexible. You, of course, don't need to do that for a lot of lines, but you can do it for any two lines, right? So it's especially important if you end up needing a conjunction. For example, in an argument like this, right, you might have A and B imply C, so you need to do this, right, to use the arrow out rule or modus ponens, you need A and B written like this, right? So if you find somewhere in the proof, say lines 5 and 6, A and and there's B. And of course they could be separated. This might be line 2, and you have a few other lines in line 6, B, aha. A and B, and they don't have to be in the order of the lines, right? You want to write your conjunction like this, A and B, right? So whatever order they show up in the lines, you can smush them together in any order. All right, so you could also do this. A, B, you could put the later line first here in your conjunction. Right? This is kind of redundant because we tell you the pattern happens whether, we did this with modus ponens, the pattern holds no matter what order of lines they are. A and B, right? Smash them together to make a conjunction. And then this is identical to this antecedent, right? And so you can infer C using another rule, okay? So there's your and in rule. Take any two lines, right? You can put an and as the main connector between them, right? If they're compound, you'd have to put them in parentheses, right? But the way the formula of the and in is, it's a two-line rule. You need separate lines. You can, but the rule is very general. You can conjoin any two separate lines, all right, in either order. Okay, I put the colon here. You should do one or the other, but I'm saying you can do either one. Okay, take any two lines, you can conjoin them. That is and in. So there's our and. How about or? Okay, we have or out is going to be the same as MTP. That's a two-line rule. That's basically MTP, sometimes called disjunctive syllogism. We're going to rename that as or out, because remember what you do. You have an or statement, and then you have a statement that half of it is false, right? And then you detach part of the or statement. So that's going to be our or out rule. Don't think I'll have room to keep writing all these rules here, but you have the sheet, and you will have the sheet with these inference rules with you for your final exam. For these and the simple derivation rules. Okay, so or out, we've already seen, that's disjunctive syllogism. A or B, it's a two-line rule. Not A, right? Half of the or statement is false, therefore the other half is true. Every time, half of the or statement is false, therefore the other half is true. Now, for our purposes, this has to be very formally correct. I mentioned this in one of our last classes, right? If this were not A, right, in this case, right, if you had this or statement, right, not P or Q, you'd want to see not P or Q, not P, right, negate the negation to follow this pattern. Well, what if I only get P? We're going to have another rule that allows you to go from P to not P. That's called double negation. I'll get to that, right? And we'll see some of this in the practice, okay? And remember, there's two forms of MTP, right? If the right half is false, the right half is true. But again, it's a two-line rule, okay? So there's your or in rule. Let me write that here, or with the capital letter I. Sorry, this is or out. Excuse me, or out. This is or out because our conclusion detaches this A from the or statement, detaches this B from the or statement in combination with another line. So that's or in. Or out is incredibly powerful. It's something that is hard to find, or it's hard to, for students to identify that they can use it because it's almost too simple. So let's talk about or out. I'll talk maybe about one application of it. Or in. Or in, incredibly powerful. Okay. Or in says, again, almost too simple to be believed, right? You can take any line and make an or statement out of that line with anything else you want. B can be any statement of your choosing. That's one of the things that makes it powerful. Because think about it. Since A is true, one of these is true. And this could be a contradiction. It doesn't matter. This could be any nonsense statement or any statement whatsoever. Because A is true, you can deduce that one of these is true, namely A. Okay? And you could of course, go in the other direction, right? Right? So this is powerful if you need an or statement. I'll talk probably in class, right, that we actually use this form of inference, right? If you reason that if either this or that happens, right, then, right, if either the Bills win or the Dolphins lose, the Bills clinch the division, right? Well, the first thing happens, the Bills win. We automatically make that inference, oh, so we met the original or condition. So we actually do make this inference quite a lot. We don't even realize we need to do it, but we do, right? So it's a powerful thing in a formal argument, right? If you get that condition, right, B or D entails that the Bills make the playoffs, for example, right? And then you get B, right? Very powerful to see that you can take this premise, B, and deduce B or D, and then you have the antecedent of this arrow statement, right? So almost too simple, and it's hard to see because you don't see the. It's hard to remember that you can just add to this statement. When I was learning this, we just called this rule addition, right? This is our or in rule. How do you introduce an or? So easy. Take any line and just make that line or whatever you want. That line is true or whatever you want. This rule is critical, something I tried to illustrate in the 3rd chapter to show you that contradictions imply any statement you like, because they're always false, right? And there's a formal derivation proof way to do that that I'll probably go over in the next video. So we have or out or in. We did and out and in. Okay, so we've got double arrows. We've got arrow out and we've got arrow in. We don't actually have an arrow in rule. Okay, we don't actually have an arrow in rule. We would need some equivalence rules to introduce the arrow. Remember, the arrow is equivalent to not or, but we don't have that, so we're not going to have an arrow in rule. So for arrow out, the way Hardegree sets it up is that arrow out becomes both modus ponens and modus tollens become arrow out. Either one, you have to follow one or the other, right? But we have, again, there are 2-line rules, A arrow B, and A implies B. Okay, this is one type of arrow out. And then, of course, we have modus tollens, A arrow B, not B, therefore not A. Okay, we've just assimilated them under the arrow out pattern because, again, you detach and negate. So we're thinking of this as a detachment or out rule. So this is our arrow out rule. We don't have an arrow in rule. We do have double arrow in and out because remember, double arrow is just equivalent to the arrow going in both directions. Double arrow in is also equivalent to some and statement, right? Either they're both true or both false, or either or statement, but we're sticking with the double arrow. So for double arrow in, let's just do double arrow out. Anytime you have a double arrow statement, okay, you can deduce that one of those arrow statements holds. Since A double arrow B, it follows that A arrow B, and it also follows, in a separate step, you could do B arrow A. Okay, that's what the double arrow is saying. A implies B and B implies A, so you can just make those deductions one at a time. So this is double arrow out. Again, detaching. We go from a double arrow statement to a single arrow, deduce a single arrow statement, so we're calling that double arrow out. Double arrow in is a 2-line, so this is a 1-line rule. Double arrow in, let me just make sure we're clear on the board here. Double arrow in, I'm going to erase this because I can't have a running list of the rules anyway. Double arrow in, how do you introduce a double arrow? Well, you find separate lines, right, where antecedent becomes consequent in this way. So if you have separate lines that say A implies B, and indeed this same consequent implies this same antecedent, you can deduce the double arrow, and you could deduce it in either order. Okay? Doesn't matter what order you put the double arrow statement in. Okay, so there's double arrow in. We got arrow out, double arrow out, or in and out, and in and out. So the only thing we have left is a negation. Our only negation rule, we don't use this pattern of in or out because it has the classic name double negation. And this tells you, this is essentially an equivalence rule. So we do this is like one equivalence rule, right? But just remember, so P is equivalent to not P, is logically equivalent to not P, and vice versa, of course. Oops, sorry, I'm off the board there. Okay, so our principle here, again, is that P is equivalent, logically equivalent to not P. Okay, so our double negation rule is that you can either tack on two negations to a whole line, almost as the main connector, just take the whole statement, put in parentheses, tack on two negations, or take them away when they're the main connector. Okay, you can also do this to part lines, but we're going to stick with this with whole lines. Okay, so the formula is just P implies not P, and likewise not P implies P. Okay, you can always take away negations in pairs. You cannot take away negations in singlets. Okay. Sometimes when students are stuck, they just start taking away negations. No, you don't want to do that. That's saying the opposite of what the statement is saying. Right? You can't just do P, therefore not P. No, that would be very bad. That would be contradicting yourself, right? But in pairs, you can do it, right? You can also add to, right? This means, remember, any statement whatsoever, right? So if you could also, I don't know why you would need to, right? But you could also tack on two negations to not P. It's equivalent to not P. Okay, I know I'm at the bottom of the board here. Not P. That's 4. I know it's a little sloppy. That's 4 there, right? So you can take any statement, tack on two negations to the left side as main connector, or take away two negations if you have two negations to take away. Right? Two negations together. Be very careful. You don't want to use double negation with a construction like this. Okay? We'll keep this. Okay. I'll go over here. Right? You don't want to do something like this. Not the case, not A and B. Okay? Okay, you can't pierce through these parentheses because this is the main connector, right? This is just negating A, right? You have to see it in a form where those two negations just work together and doubly negate a statement, right? So you do not want to do that for here. You don't want to just make this equivalent to A and B, right? And indeed, if you think through some of our equivalence rules, this is not equivalent to A and B, so you don't want to do that, right? Make sure it's on record in the video. Bad. Okay, so when you see it's got to be two negations that are together, right? The same unit negating the same thing. Again, for now, you should think of it only when two negations at the end are the main connector statement. You can actually apply it to parts, right? Where you have not P or Q, you could just turn into P or Q. I don't think you'll need to do that. I think we're kind of treating these as whole line rules. Notice this is, again, a one-step rule, right? Right? Take any line, you can tack on two negations. If you have two negations, you can take them away. This uses the fact that every statement is a negation of another, right? So when you have P or not P, right, these are opposites, right? We can represent, the reason we allow double negations is to represent that this P is the opposite of this. This P is the same as saying not P is false, right? So we kind of, in positive statements, you have, so to speak, these two hidden negations. It's negating, it's a negation. Sorry if that was right, but they're opposite, so that's why we allow these double negations. Okay, those are the rules. I think they'll pin down better if we do some practice, so I'm going to practice some exercises in another video, and those will be our videos for direct derivations.